Okay, Assalamualaikum. So for today, I will do some analysis on the diesel cycle question. So this is a standard final exam question for diesel cycle, which is also called as the idle cycle for compression ignition engine. So I will read first this question. Okay, so basically this is I take from your notes lah. Right, change a little bit of the layout first. I can reduce the spacing here. Okay, so proceed. An ideal cycle has a compression ratio of 17 and a cut-off ratio of 13. At the beginning of the compression process, the temperature and pressure of the air are 37 degrees Celsius and 100 kPa respectively. If the mass of air is 0.1 kg, showed all the processes on a PV diagram and determine. So that is all of the question listed. So when you got this kind of question, first identify what is the kind of cycle. So this is the diesel cycle. This is your compression ratio, which is RV, and then followed by the cut-off ratio 1.3. This is your RC. Then at the beginning of the compression process, the temperature and pressure of the air are 37 degrees Celsius and 100 kPa. So this is the beginning. If the mass of air is 0.1 kg, show all the processes on a PV diagram. Right. So when you get this kind of diesel cycle, which means that you need to identify or plot the PV diagram here first. Okay, no need to confuse with other modification, because when you know this is a diesel cycle, just straightforward sketch the PV diagram. Okay, and then draw the curve line here from 1.1 to 0.2. Then this is the isentropic process, followed by the constant pressure process here, and then followed by the isentropic expansion till it's reached the state 4. Then go back to state 1 to complete the cycle. Okay, so this kind of diesel cycle PV diagram is same as if you face a diesel cycle. This is the only PV diagram that you need to know lah. Right, so now put all of the information here, which is from the question. For example, here we have a cut-off, the compression ratio of RV listed here. RV as equal to V1 over V2. This is equal to 17. Right, so since this is a diesel cycle, this is the typical value for the compression ratio for diesel. For auto cycle is much lower lah. And then cut-off ratio of 1.3. So this is your RC, which is equal to P3 over P2. So this during the constant pressure heat addition process, this is equal to 1.3. Just to mention that you need to also put some indicator so that you know where is the location of the heat addition and also heat rejection process. Okay, so this is your Q in, also this is your Q out. Alright, and then at the beginning of the compression process, the temperature and pressure. So temperature at the beginning is 37 degrees Celsius. So this is your T1. 37 degrees Celsius. Okay, so remember, if you deal with gas, just change into a Kelvin. Okay, the unit must change into the Kelvin so that you can use the ideal gas equation easier. Right? 37 plus 273, this is equal to 300. Sorry, it should be 310. Okay, and then what else information here? 100 kPa. This is your P1 equal 100 kPa, and then it was given 0.1 kg as your mass, and then That's all the information that we get. Now is the process to solve the problem. So remember, for a gas, you need to get all of the temperature at each point. So that is the first objective of this kind of cycle. Because when you get the temperature, you can find other information such as the heat addition, also heat out, and also the net power output produced by this kind of cycle. So we start with state 1 here. I put right. So given just now T1 equal 310 Kelvin, and we have P1 equal 100 kilopascal. Okay, so this is settled. Now we move to state 2. So in order to find state 2, 1 to 2 is a process of isentropic. So you need to know the link between these two is isentropic process, so that you can use isentropic equation to get the properties at state 2. But first, look at state 2. Is there any information given here? So there's no T2 or P2, but we know that this is, we have the V1 over V2 here, so we can use this value, this information to get the properties at state 2. Okay, so in order to use this V1 over V2, we can use the isentropic equation. We have 3 equations. The first one is about T2 over T1 equal P2 over P1 K minus 1 over K. So this just link temperature and pressure, but this will not helpful in this kind of cycle because we do not have much information. Okay, for example, here we have 2 unknown, which is T2 and P2, which is the unknown that we need to solve. However, we only have 1 equation, so this will not help. And then we need to use another isentropic equation, T1 V1 power of K minus 1 equal T2 V2 power of K minus 1. So we know that we have 3 unknown here, V1, V2, and also T2. But since we know that the ratio of V1 over V2, which is equal to 17, so the only unknown that is remaining here is only T2, because we already have T1. Okay, so we can use this equation to solve to get the T2. Right now I will solve this using this equation. T2 over T1 equal V1 over V2 power of K minus 1. So I just rearrange this equation here, and then your T2 equal to T1 V1 over V2 power of K minus 1. So this is equal to your T1 just now is 310 Kelvin. V1 over V2 is 17. Your K is equal to, you use the K for air. So this equation already give the value of K, or no, but it gives you the value of Cp and Cv. So K basically is equal to Cp over Cv. We can use that value. Maybe I can put here. Right, K equals Cp over Cv 1.005 over 0.718. This is equal to 1.4. Okay, so K minus 1, 1.4 minus 1. So you just punch your calculator and you get the answer for T1. Right. So equal to, I need to use my Excel because I don't have my calculator here. 17.4 times 310. Okay, maybe I can find my calculator here. where's my so we have here 17 power of 0.4 multiply with 310, so you get here 962.8 Kelvin. 962.8 Kelvin. So make sure you maintain a 4 significant figure here. 962.8 Kelvin is enough. Right now we are moving to state 3, or you can also refer to the question if it asks for the pressure. So if you use this question A, it asks for temperature and also pressure. So so now we have T2, right? So you can go back here to get the value of P2 since we know the value of T2, or you can find another isentropic equation that relate pressure and also volume, which is P1 V1 power of K equal P2 V2 power of K. So we already know P1, we already know the ratio of V1 and also V2, so the only unknown is P2 here. So P2 equal to P1 V1 over V2 power of K. So this is equal to 100 kPa multiplied with V1 over V2, 17, this is 1.4. So again, punch your calculator here. 17 power of 1.4 equal to multiply with 100. So you get here 5279.9 kPa. 5279.9 5279.9 kPa, or you just can write as 5280 kPa. Okay, so this is your P2. Now we move to state 3. Okay, state 3. Right, to relate state 2 to state 3 here, we know that the process between this is isobaric. So since this is isobaric, you can look at this equation, this diagram, PV, constant pressure process. So what is the exact equation for this? For isobaric, you cannot use the isentropic as previous we do during to relate state 1 and state 2. So we need to use isobaric equation. So for isobaric, just look at the traditional equation, PV over T from 2 to 3, and then we know that P2 and P3 is constant, so you left with V2 over T2 equal V3 over T3. Okay, so because this is isobaric, this is the only parameter that left in this equation. V2, T2, V3, T3, right? So sorry, for the cutoff ratio here, and just notice here, this is not P3 over P2 but V3 over V2. So since the pressure is constant, so I'm sorry, this is V3 over V2. Okay, so this is the how much the volume is deviate during the constant pressure process. So in this equation, we want to find T3 because this is the only parameter that left in this equation. We already know T2 and the ratio of V2 and also V3 already know. Okay, so you just rearrange T3 equal to T2 times V3 over V2. Okay, so basically this is equal to T2 RC, times RC, which is your cut-off ratio, RC. So your T2 just now we calculate as 5279.9, sorry, 962.8 Kelvin. We multiply with the ratio, cut-off ratio here, 1.3. So get the value as 962.8 times 1.3, so 1251.6 1251.6 Kelvin. So this is the highest temperature when you deal with this kind of diesel cycle, right, in this equation. So now how to find the pressure at state 3? Okay, so the pressure at state 3 basically is similar with pressure at state 2 because this is isobaric. So just write this as 5279.9. Make sure all of the parameter that you write, you mention about the unit. You use the correct unit. Now move to the state 4. Okay, so from 3 to 4 here, this is the isentropic process also. So you can use the isentropic equation to find the parameter at state number 4. Okay, so first you can link between 3 to 4 with TV. T4 over T3 equal, sorry, let's use this T3 V3 power of K minus 1 equal T4 V4 power of K minus 1. Okay, so we want to find a T4 here, but we need to look whether we have the value of V4 over 3 or we don't have it. Okay, so since V4 over 3 is not directly given in this kind of equation, okay, so I think this T3 V3 we can find using another method, right? By using the some we call as a chain rule to find the ratio of V4 over V3. Maybe you have been heard about this. Okay, V4, right? So I rearrange first the equation because our target is to find T4. Okay, T4 equal to T3 times V3 over V4 power of K minus 1. V3 over V4 power of K minus 1. Okay, so since we do not know the V3 over V4, we do have T3. Okay, we have calculated before. So in order to find V3 over V4, we use chain rule. Okay, what is chain rule? Chain rule is some mathematical operation to get this ratio by relate it with another ratio. So in this case, V3 over V4 equal to, okay, so how we want to apply this? So you just find the nearest ratio of 3, which is V2. 3 and 2 is the nearest point, and then you multiply with this is the denominator V2. You multiply with the same value here, V2 also, and then you divide with V4. Okay, so what happened here basically is just some mathematical modification to relate 2, 3 and 4. So if you just focus back on this, you will get this ratio back, V3 over V2 times V2 over V4. Okay, so since V4 and also V1 is constant, right here, look at the diagram, the volume here is constant, V4 equal V1. Okay, but V3 is not constant as V2, so you cannot do the similarity there. So you can replace this with V1. So here V3 and V2 is different value. Okay, or we can call this as the cut-off ratio, RC. This is your RC. Multiply with V2 over V1. So this is your 1 over RV, 1 over your compression ratio. So recall back, your compression ratio RV equal to V1 over V2. You can look back at the above here. Okay, RV equal V1 over V2. So this is just some mathematical expression to relate RC and RV. Okay, so since we know the value of RC, which is V3 over V2, which is 1.3, multiply with 1 over RV is 1 over 17. So the ratio here, V3 over V4, actually is 1.3 over 17, 0.0647, 0.07647. Okay. Okay, remember to use 4 significant figure here. Alright, so now put another page here to continue my answer. We can use this 31 over 17. We can use this to calculate back our T4. Okay, so I get back this T4 equal to T3. Our T3 is 1251.6 Kelvin. You multiply with the ratio here, V3 over V4, 0.07674, power of K minus 1, 1.4 minus 1. Okay, again punch your calculator and you will get the value of T4. Zero 0.07674 power of 0.4. Okay, you multiply with 1251.6, so you get here 448.2. 448.2 Kelvin. And then the last one is to get a pressure at state 4, P4. Okay, I also relate with the previous equation. P3 V3 power of K equal to P4 V4 power of K. So you can use or rearrange back the equation. P4 equal to P3 V3 power of V4 power of K. Okay, so since we already know the value of V3 over V4, just now we get 0.07674. Your P3 is the 5279.9, which is similar with P2, 0.07674 of 1.4. So you get here 145.1 kPa. Okay, so that is the all of the temperature and pressure from state 1 to state 4. Okay. Alright, now look at the question. Okay, so at the question here, we already answered question A. Now find question B. So this is just the extension of the question. So this is the heat addition during the constant pressure process. So during the constant pressure process is here, from state 2 to state 3. Make sure you know what is the unit that the question wants. So since this, it asks you in kilojoule. Okay, so we need to find Q23, big Q23, since it asks you unit in kilojoule. So the small q, we just use Cp, since this is a constant pressure, T3 minus T2, so Q23, or this is a Q in set. But since we want the unit in kilojoule, means that we need to multiply with the mass here. Okay, otherwise you just get the unit in kilojoule per kilogram. So make sure this is unit, because this is a constant pressure process. Okay, so the mass given in the question is m equal to 0.1 kg. The Cp is 1.005, so we just use here 0.1, right? Okay, 0.1 kg, Cp is 1.005. Okay, T3 is the maximum temperature. Just now we get as 1 to 5, 1.6 minus with the T2, which is 962.8. Okay, and then you punch a calculator, then you get the answer. Got here 29.02 kilojoule. Okay, and then the next question, the work net output. Okay, so the work net output, the unit in kilojoule. Okay, so we need to find the work net, which is for this kind of cycle is equal to Q net, which is Q in minus Q out. So since we already calculate the value of Q in, just need to find the value of Q out. So your Q out is from state, okay, here 4 to 1. Okay, 4 to 1. So this is from 4 to 1. So since this is a constant volume process, okay, so look at the diagram again. Make sure that is a constant volume from 4 to 1. Yes, V4 equal to V1. So you need to use CV. And then T in minus T out, T4 minus T1, because T4 is higher than T1. Okay, and then you need to multiply with the mass, because it asks the unit in kilojoule also. Okay, now M 0.1 kg, CV is 0.718. Then your T4 just now we calculated as 448.2, sorry, minus T1 is 310 Kelvin. Okay, again punch your calculator. 448.2 minus 310 equal times 0.718 times 0.1. You get here 9.923 kilojoule again. Alright, so now calculate the work net produced Work net is equal to Q in minus Q out. So you get your Q in calculated 29.02 kilojoule minus 9.923 kilojoule. Again, calculator, 29.02 minus 9.923. So this is equal to 19.097. Okay, so this is your answer for work net. So question C answered. The thermal efficiency is calculated by analyze the work net, or you find the work net over the Q in. Okay, so what is the work net? You calculated 19.097 kilojoule, divide by your Q in, 29.02. So you just punch your calculator and get the answer easily. Hmm. 19.097 divided by 29.02. You got here 0.6580. But if the question asks in percentage, you need to change into percentage. So just multiply with 100%, 65.8%. Okay. Now look at the last question. The mean effective pressure. So this is just the average pressure when this cycle is operated. So in order to get the MEP, the unit in kPa, okay, you need to find the volume. The volume. So the formula is given as MEP. Let's say you want in kPa, you need to use the kPa value for work net. Work net divided by the maximum volume, V max, minus V minimum. Okay, so make sure your unit here, if you want to get kPa, the unit here in kilojoule. Okay, this one is in meter cube. If the above one, the former is in kilojoule per kilogram here, which is small w, the latter or the bottom one you must use in meter cube per kg. Okay, so I will use the first one since we already calculate the kilojoule. So how to find V max and also V minimum? So this basically is represent your V1, this represent your V2. Okay, so if you recall back your diagram here, I copy here. Okay, the position of V1 is here at state number 1, while the position of V2 is the minimum volume. Okay, so how to find 1 and 2? We just use the ideal gas equation. P1 V1 equal MRT1. Then you just rearrange V1 equal MRT1 over P1. So your M is 0.1 kg. Your R for air is you can look back the information given here, or you can look at the property tables. The value is 0.287. 0.287 kilojoule per kg dot Kelvin. Your T1 is 310 Kelvin. Then your P1 is 100 kPa. Okay, so just use your calculator again. 0.1 times 0.287 times 310 equal, divide by 100 equal 0.08897 meter cube. So this is your V1. And then since we know the value of compression ratio RV equal to V1 over V2, you can use the similar with big V here, V1 and also V2. So V2 equal to V1 over RV. So 0.08897 meter cube. You divide by the value of RV, which is 17. So you get here 0.08897 divided by 17, 0.00523 meter cube. Okay, so then you plug in into the formula of the MEP here. MEP in kPa equal to, your work net is equal to 19.097 kilojoule over V1 0.08897 minus 0.005234. Make sure you use 4 significant figure here. Okay, so now just punch our calculator. 0.08897 minus 0.005234. Okay, so 19, sorry, 0.08897 minus 0.005234, 0.083736, 19.097 again, 19.097 divided by 0.083736. So you get here 228.1 kPa. Okay, so this is the mean effective pressure, or it just looks like the what we call as the average operating pressure during this cycle. So basically, if we want to illustrate this in your PV diagram here, okay, so I just adjust this thing. The MEP basically is the area enclosed by this cycle. So because the area is quite difficult to calculate because it have a curve, so that we just use the formula of MEP equal work net V1 minus V2 to represent this area by imitating or replicate it into a rectangular. So this rectangular basically is just shift this area into this value. So this is your MEP value. We calculate as 228 kPa just now. So this is the head here is your MEP. The width here from here to here is your V1 minus V2. So basically what is enclosed by this curve is your work net. Okay, so if you just rearrange back this equation, work net equal MEP times V1 minus V2. So this is the head of this diagram. This is the width of this diagram. Okay, but this is the formula. Normally we want to find the operating or mean effective pressure of this cycle. Okay, so that's all for now. So this is the diesel cycle. I will show also on the dual cycle. Okay, thank you very much. Assalamualaikum.